Hello everyone, welcome back to our AI project series. I'm Priyambada and today we are diving into the fascinating topic of electric vehicle routing problem. I along with my teammates Manoranjan Singh and Shweta Kumari, we are diving into the new problem statement. Before we start, if you haven't watched our last lecture on PhD learning, make sure to check it out from the link in the description below. It covers some essential machine learning theory concepts you will find helpful for optimization based problems like this one. Let's jump and start the session. For the contents, we have introduction to EVRP, problem description, objectives, algorithm implementation, city network details, energy and distance calculation, algorithm-wise best solution, performance comparison, key observations, conclusion, future work, and references. So let's dive into this session. So what exactly EVRP is? Well, it's an advanced extension of the classic vehicle routing problem, except this time we add in the constraints for the battery management and charging station availability. The goal is to efficiently manage a fleet of electric delivery vehicles in a city, ensuring they recharge on time and cover all delivery points without running out of battery. And of course, we also need to optimize route efficiently. So let's understand the problem description. What exactly EVRP is, we have understand it, and now let's come to the problem statement. Imagine the city as a network graph consisting of central depot, customer locations, charging station. Every EVRP starts fully charged and before its battery drops below 15%, it must recharge. But charging stations have limited ports, so vehicles may need to wait in a queue. Also, the energy consumed depends on how far the vehicle travels and the load it carries. A constant energy rate alpha calculated using the formula energy equals alpha multiplied by distance multiplied by weight. What is our ultimate aim? To minimize energy use, total distance, and total delivery time. Let's go through the objective part. Now let's talk about the core objectives. There are three goals here. First, minimize total energy consumption while completing all deliveries. Second, minimize the total distance traveled by all vehicles. And the third, minimize overall delivery completion time, including any delays at charging stations. Achieving all three together makes this problem quite challenging, and that's what makes it interesting. So let's see what algorithms we implemented in this. To tackle this problem, we experimented it with 6 different algorithms. First, the heuristic search, a quick rule-based method. Genetic algorithm, an evolutionary optimization technique. Second, simulated annealing, which sometimes accepts worst solution to avoid getting stuck in local optima. Tabu search, a memory-based local search that avoids previously visited paths. Ant colony optimization inspired by real ant behavior using pheromone trails. And constraint satisfaction problem, that is a CSP, perfect for handling strict constraints like battery levels and charging station limits. Each has its strengths and weaknesses. We will see later in the results. Let's see about the city network details. Here is how city network is structured. The depot is starting and ending point for all vehicles. Green nodes mark charging station, blue nodes are customer delivery points. The edges between them represent the distances. Key constraints to remember. EV must recharge before battery drops below 15%. They start fully charged and must return to the depot after completing the deliveries. And there is a limit charging capacity at each station, meaning vehicles might queue up. The city network's setup combined with these constraints makes route planning a multi-objective, multi-constraint optimization problem. And now I will hand over the session to Shweta. Thank you.
Thank you, Priyambada. Let's have a clear look at network graph itself. In this graph, red node is our depot, green node are charging station, blue nodes are customer points. The connection between them or edges represent the actual distance between two locations. This graph layout forms the basis for all our route planning, and our algorithm will use this structure to decide which delivery points to visit, when to recharge, and how to minimize energy use while completing all deliveries. Now comes to the slide energy and distance calculations. Now let's move on to how we calculated energy consumption and travel distance. For every trip between 2 points, the energy consumed by a vehicle is calculated using this formula. Energy consumed is equals to alpha into distance into load, where alpha is a constant energy rate, distance is the distance between 2 points, weight is the cargo weight currently being carried. As deliveries are made, the load reduces, which in turn decreases the energy consumed for the next travel segments. Now, each vehicle must plan its route such that it never drop below 15% of battery capacity before visiting a charging station. This constraint is not just a check, it's actively modeled inside our optimization algorithm. Now comes to the slide SAT and CSP constraint modeling. To properly handle these energy and routing constraints, we approach the problem using two powerful frameworks, constraint satisfaction problem models and SAT solver formulation. In our CSP model, we define decision variable like which node a vehicle visit, when it recharges, and how much energy it has at every point. Constraints ensure that a vehicle only visits customer points once, follows the depot start rule, never exceeds capacity, and recharges before hitting the 15% threshold. In SAT formulation, we encoded variable like xijt for whether I travels from node J to node T, and EIT for vehicle energy at time T. Then we wrote logical constraints in Dinkus CNF format to be passed to a SAT solver. For example, if a vehicle travel from node J to T, its remaining energy at T must be at least 15% of the total capacity, or it must visit a charging station before proceeding. By integrating these constraints inside our optimization algorithm, we ensured that every route solution was feasible under energy limits and charging station. As we can see in the slide, total distance for the vehicle K is equals to summation of I equals to 0 to n, summation of j equals to 0 to n, d of ij into xijk. Now comes to the slide, the EVRP algorithm-wise best solution. Once we had our CSP and SAT models ready, we tested multiple optimization algorithms to see which one produced the most efficient route. We tried Heuristic Search, which is quick and rule-based algorithm, genetic algorithm, which is population-based evolutionary optimization, simulated annealing, which is a probabilistic technique to avoid local optima, Tabu Search, a memory-based local search, and colony optimization, which is inspired by how ants find food using pheromone trails. CSP solver to directly find constraint satisfying solution. Using all these algorithms, we find the best route through it. Okay, the result of heuristic and colony optimization constraint satisfaction problem approaches consistently produce the most efficient plans. Total distance around 90 km, total energy consumed around 900 units. Genetic algorithm simulated annealing and Tabu Search explored larger solution spaces and provided feasible but less optimal solution with higher distance and energy use. These results highlighted the importance of choosing an algorithm suited to your problem size and constraints complexity. Now comes to the slide performance comparison. Now let's compare how each algorithm performance on three key metrics: total energy consumed, uh, execution time, total distance traveled, okay, and the total time. Heuristic Search and CSP were the fastest, completing instantly while giving the best solution. ACO, that is, and colony optimization was slightly slower due to its iterative pheromone based update but still gave near optimal results. Simulated annealing and Tabu Search took a bit longer, around 0.038 seconds, because of their iterative nature. Genetic algorithm performed the slowest and produced the highest total distance and energy consumed, indicating a need for better parameter tuning. In conclusion, for our problem instance, heuristic, CSP, and ant colony optimization were the most efficient choices. And now, to summarize some of the most interesting insight we gathered from these experiments, let's hand it over to Manoranjan. He will explain the further slide.
Welcome back, guys. Now we are looking into key observations. Point number one: heuristic ACO CSP algorithms consistently produced the most efficient routing plans with the lowest total distance 90 km and the lowest energy consumptions 900 units. Genetic algorithm, simulated annealing, and Tabu search explored a much larger solution space, resulting in higher total distance and energy cost, but offered alternative feasible solutions for complex scenarios. Execution time, heuristic and CSP were instantaneous, zero point 0.0 seconds. ACO maintain a comparative balance between solution quality and execution time. Essay and Tabu search require more time due to iterative and memory-based search strategy. Point number 4, ACO matched the optimum routes of the heuristic and CSP but the slightly higher execution time, showing promise for scalable cases. Point number 5, GA performed the worst in the instant, generating the highest total distance and energy, indicating it may need better Turing or long generation for convergence. For small to medium sized city networks, simple heuristic and CSP formulations can be highly effective and fast, while meta-heuristic like ACO and Tabu search remain viable for large, more dynamic systems. Now coming to future work, scalable to large network, expand the current EVRP model to support large, complex urban network with increased customer need nodes and charging stations. Dynamic demand and real-time data. Incorporate dynamic pickup and delivery request, fluctuating energy cost, and real-time charging stations availability in routing decisions. Incorporating of time windows. Integrate customer time window constraints and charging stations operational schedule to simulate practical and real-world scenarios. Multi-objective optimization. Simultaneously optimize for total distance, energy consumptions, operation cost, and every time using advanced multi-objects algorithms. Now coming to the conclusion of all this all. The electric vehicle routing problem, which is also known as EVRP, poses a significant challenge due to constraint on vehicle capacity, energy consumptions, and choice availability. Among all algorithms tested, heuristic and colony optimization, which is also known as ACO, or CSP approaches provide the most efficient solution in terms of total distance, total energy consumption, and especially for small scale instance. Meta-Heuristic algorithm like simulated annealing, Tabu Search offer alternative routing plans with a reasonable performance but a high computational cost. Genetic algorithms show at least effective performance in this scenario, indicating a need of parameter optimization and long run for improved solutions. References, here are some references. Joki D and Seder M in 2015, they made a routing of fleet of charging electric vehicles in a mixed vehicles fleet constraints. There are several things you can see. Okay, now thank you for this.